Well, good evening, everyone. This is the sixth webinar in the series that I'm presenting for the Deep Reinforcement Learning Nano degree for Udacity. And today's webinar is about convolutional neural networks and how these networks are used to generate features for the state space inputs on a deep reinforcement learning problem. So with that, let me share the screen and we can get started. Okay, so the week 6 webinar. The objectives this evening are to provide some insight on how convolutional neural networks are used in deep reinforcement learning. Also compare and contrast these way that convolutional neural networks are used in deep reinforcement learning compared to traditional supervised learning. Most of the information in today's webinar came from a blog called Towards Data Science. This is a great blog for all things data science related, including neural networks and deep reinforcement learning. And I have the URL there listed if you want to go and get some more details on what I presented today. So let's start by talking about convolutional neural networks as you probably have used them in the past for image classification. And then we'll contrast this with deep reinforcement learning at the end. But this gives a good some background information, a review of convolutional neural networks in general. So this is the pipeline for a traditional convolutional neural network classifier. Typically, there's an input image that can have multiple dimensions. For example, if it's an RGB image, you'll have a channel for red, a channel for green, and a channel for blue. So it'll have a depth of 3. Sometimes the image could be grayscale, where you might just have a depth of 1. Or you could have perhaps grayscale with some history to detect motion in an image. And you may have different times that the data was collected. So you could have a depth of 4 or 8 to collect the last 4 time steps or last 8 time steps of data. So that imagery information is input into the convolutional neural network. And then it goes through a pipeline with a series of convolutions with ReLU typically, activation function applied, and then some type of pooling, either max pooling or average pooling. Usually max pooling, but sometimes average pooling. This is repeated any number of times. And you notice as you go through this pipeline that initially the image was large dimensions in X and Y and typically not very deep. And as it moves through the pipeline, it successively gets smaller in the X and Y dimensions, but deeper in the number of features that are collected and available for input to the classification. So that's kind of depicted in the drawing here of the different basic sizes of the volumes of the cubes there. So you see the volume of the cube on the input is wide and in the length and the height dimension, but not very deep. And by the time you get to the end, you have a lot of outputs for the classification, a lot of features that you've collected. So it's very deep, but each one of them is typically fairly small. Then at the end of that pipeline of convolutions and max pooling, all the data is flattened. That basically means take that whole volume of that cube and basically just pull every entry out of that cube and line it up into a one-dimensional vector. And that 1D vector at this point can be quite large. It's not unusual to have 2048 or 4096 or more different inputs after it's been flattened. And then the data then goes through a set of fully connected layers, a traditional feed-forward fully connected network, at the end of which the outputs contain all the different features, all the different items that you want to classify. And usually a softmax activation function is used at that output so that you get the probabilities that that input image corresponded to any one of those individual output neurons. So that's the traditional way that convolutional neural networks are used in a classifier system. We'll see that in deep reinforcement learning, you'll see sort of a similar, especially in the front end of this, a similar way that this is done for extracting features for input state information for a deep reinforcement learning problem. So now just a quick refresher on basic convolution and max pooling kind of operations. I'm sure you have all seen this in some earlier classes in neural networks. I assume by the time you take this deep reinforcement learning nano degree that you probably have been introduced to this from a regular deep learning program of some sort. So I'll go over this fairly quickly, but the basic idea on convolutions is that you take the input image and you have a convolution filter. The image in this picture on the right is the green full-size image. The convolution kernel or filter is the smaller 3x3 that you see in the upper left corner of that image. And the kernel has the little red numbers by 1, by 0, by 1 in the first row, by 0, by 1, by 0 in the second row. Those are the values of the kernel, and the image is the larger values. So you place the kernel in the upper left corner of the image, and you multiply element by element the kernel by the input image, pixel by pixel. Add each of those up. So in this case, it's a 3x3 kernel, so we'll have 9 separate numbers that will then add up. And the addition of all of those added together becomes the total for that first upper left corner of the feature, output feature. So once that first element has been determined, then you slide the filter over by 1, or actually just by the stride length, but typically 1 or 2, sometimes 3. And you perform the same action again. So as the filter slides over, the input image stays the same, but the filter is overlaying a different area of the image. And so the multiplication of the filter elements by the corresponding underlying image elements produce a different multiplication sum total. And that product goes in the second top square of the convol feature. And then you again move the kernel over one more and repeat. Once you reach the far end of the image, then you slide the kernel down and push it all the way to the left and continue on doing the same actions all the way across the image. So the end result is that you get a convolution of the filter across the entire image, and the result of that convolution is some sort of a feature that's kind of dependent on the characteristics of the filter that you have, the kernel that you're using. Now in the deep learning system, these kernels are actually learned. So initially they're just randomized to be some random sets of values, but as the classification takes place and the supervised learning operations take place, then the thing that's being learned here is the right set of kernels to use to extract a reasonable set of features that can perform the classification. So again, this is sort of the same thing we just talked about, but highlighting a couple different things. You can see the squiggly lines on the right just shows how the kernel is slid to the right, comes back to the left edge, slides across again, and you continue that till it gets from the upper left corner all the way down to the lower right corner of the image. The second important thing is that you have to remember that the kernel size, the depth of the kernel is the same as the depth of the input imagery that you're processing with the kernel. So if you have for example, an RGB image with 3 layers of imagery, then your kernel also has 3 layers of depth to it. And a 3x3 surface kernel actually has 3 sets of those 3x3 kernels that are individually applied to each of the corresponding input imagery features that you apply the filter to. And this kind of just reinforces that. Here's a example of 3 input channels with red, green, and blue, and then a filter that's 3x3 that also has a red, green, and blue component. And the red part of the kernel is applied to the red channel of the image. The blue layer of the kernel is applied to the blue layer of the image, and the green layer of the kernel is applied to the green layer of the image. Each of those kernels individually slide across the multiplication pixel by pixel, and then add them all up for each one of the places where you place the kernel. And then the output actually that you produce is just a single channel, and that final output feature is the summation of all 3 of those kernel imagery channel convolutions. So quite a bit of processing takes place just to get one output element in the feature output space. So now on to the next major part of a convolutional neural network is a pooling layer. In this case, I'm showing max pooling. So here we have an image on the right that has a set of pixels of the values 33210, for example, in orange. And if this is a 3x3 max pooling, then you'll place a 3x3 max pooling. You can think of it as a filter over the upper left corner, and you look at all of the values that overlay that max pooling kernel and pick the maximum of all those values, and that becomes the value of the output. And then you kind of do the same thing as you do with the convolution. You slide it over and again do the same action. Typically, the stride of this can change. Often it's 1, sometimes often it's 2. 2 is a very common value for the stride, where you slide it over 2 at a time. Sometimes 3 or 4, or some other value. It's kind of up to the engineer designing the neural network to pick it's sort of an art to pick the way that you want to have stride values both for the convolutions and for the max pooling. And the larger the stride, the more you'll reduce the dimensionality of the output compared to the inputs, but also the less of the information that you'll be able to extract as you try to produce reasonable features. So it's always a trade-off there. So why do you do max pooling? Well, first of all, one of the major reasons is just to reduce the computation burden. So as you reduce the dimensionality of the feature space, then subsequent layers of the pipeline have less and less to work with. So that helps to reduce the amount of time it takes to process this data. It's also, especially in max pooling, it's a way to extract just the dominant features. Features that aren't as dominant sort of get lost. It suppresses noise. Especially if you want to use an average pooling, would suppress noise probably more than max pooling, I think. And one important feature is it does provide some translation and rotation invariance to the features that you're extracting. So that's of all those things, probably the two most important is reducing the computation burden and providing that translation invariance. For a classifier problem, that's especially as important because your training set may have training images in certain locations in an input image, and when you go to actually apply your neural network to a real world image, that image you're trying to classify, it may not appear exactly in the same place in the frame. So you want to have that translation and rotation invariance to give some flexibility of your network to recognize and classify lots of similar images in the real world that were seen in the training set for supervised learning. So as I mentioned, max pooling is probably the most common one, but occasionally you'll also see average pooling. I might just mention before I leave that the only difference between those two is that for max pooling, you take the max of the values that the pooling filter overlays, whereas for average pooling, you'd average all those together to get that one output image, that one output feature pixel. So everything we talked about so far is kind of on the left half of where all these rectangles are on this diagram. That takes the input volume of the input imagery, performs all the convolutions and max pooling that you would apply. The last half is the classification set, and that is once you've got the features identified through convolutions, those will all be flattened to produce a standard feed-forward, fully connected neural network. And as I mentioned before, you could have any number of layers here. And the output layer would have one neuron for every class that you would classify to, and typically use a softmax activation function so that the outputs are the probability of finding of identifying each of those classes in the input imagery. So just as an example here on a traditional neural network, convolutional neural network, MNIST is a very common first principle look at this. It's sort of the classic example problem. So here, the input images contain a set of digits that were obtained from like zip code data from the post office. These were extracted, and this was trained. This network was trained to recognize those digits. So here, the input image is a very small image. It's a very simple problem. This was initially done many years ago when we didn't have fast GPUs and multiprocessor systems. So this might have been a challenge back in the day when this was first used in this application. Today, this is a pretty simple problem, but because of the computational complexity of the problem as it was seen then, the input images were fairly small, and the number of features extracted inside the network was fairly small all the way along the line. So here, the input image was a grayscale image. It was only 28 by 28 by 1 because it's grayscale. Typically set through the convolution and max pooling layers, as we talked about, then flattened into the green elements. Here we just have a single hidden layer, but typically you would have 2 is very common, occasionally 3 hidden layers. And then the output here, again, since we're recognizing digits, the outputs in this case are those orange output neurons at the far right. And there's one for each of the 9 different or 10 different digits that you could have, 0 through 9. And again, softmax activation on that output layer. So the important part of this really is the fact that all the convolution and max pooling layers, the purpose of that is to produce a set of features. And once those features that characterize the input data have been established, then those features are used as input to the classification. So the fully connected layer does the classification based on those features that were extracted using convolutions and max pooling. So now let's talk about how convolutional neural networks are used in deep reinforcement learning. It's very similar for the most part. A couple of small differences, perhaps. I should mention really right off the bat, before we even talk about the table here, that the main purpose of a convolutional neural network in a deep reinforcement learning problem is to take an input space that consists of imagery typically, and instead of having many, many pixels of imagery being fed into the input as a state data, to try to extract features that give some higher level features, a better characterization of the input space, and a less dense input to the environment for the agent to learn from. And by learning from these features, the agents will have a much easier time than if you tried to just learn directly from the raw pixel data. So this is a famous paper by Min et al., where they took a set of 49 different Atari video games and created a deep reinforcement learning environment and agent that could recognize those input images and make decisions on them and navigate that environment to play those games. They basically learn how to play the games just by looking at the input imagery. And this was the general setup of Min's networks. You notice it has 5 layers. There's 3 convolutional layers, and kind of one important thing is the initial input imagery here is 84 by 84 by 4. So what they did was they took the original Atari game screen, converted it to grayscale, reduced its dimensionality to 84 by 84, and then took 4 successive time steps of data in order to let the environment have a history of where things were happening to capture motion characteristics. So that first convolutional layer is input is 84 by 84 pixels by 4 depth of the and here the depth is time. The second convolutional layer has another set of filters. The third convolutional layer, a third set of filters. And notice that the input started out as 84 by 84 by depth of 4, and the output of all these convolutional layers is only a 7 by 7. Every feature that it has here is now 7 by 7 in size, and there are 64 different copies of those features. Those all get flattened and put into a fully connected layer, and a second output fully layer that has 18 filters, 18 outputs. Those 18 neurons in the output are basically the different things that you could do in an Atari game, the different actions you could take. So essentially the input was the 84 by 84 grayscale images, and the output are the 18 different things you could do, like push a joystick up, push it left, push button A or B, or the different buttons you could have in all the different games. And again, there were 49 different games, I believe, that they applied this to. So that number 18 comes from all of those games, all the different variations of actions that you could take in any one of those games. And they used that same network without any changes in the architecture. They retrained each, they started with the same architecture and applied the same neural network deep learning algorithms, and just went through the learning process and learned every one of those games with the same network architecture. It was a pretty amazing thing for its time, which actually wasn't that long ago. It was only 3 or 4 years ago, I think. So it sort of kicked off this whole field of deep reinforcement learning for what might be considered real world kind of problems. This is just a different view of that same information. The input layer containing the 84 by 84 images with 4 frames, and going through the convolution and max pooling layers to the fully connected layer at the end with the output neurons being the actions that you can take. So just a different view of the same thing. So again, the main idea is that we want to be able to take those images and convert them into a state space representation that can be input to a deep reinforcement learning environment. So this evening we just really spent some time on looking at traditional neural networks and how the convolutional layers and max pooling layers are interleaved to extract features, how that output set is flattened to feed into fully connected layers, and then softmax classification. And very similar situation with deep reinforcement learning. Input images represents data information, use convolutions to extract features, and fully connected layers select actions. Now you would use probably like for a value network evaluation, you wouldn't have the convolutional neural networks in that type of a network, but later on when you talk about actor-critic networks, for example, an actor network might have a convolutional neural network as an input to extract those features. One thing I meant to mention that I didn't is that one of the differences between a traditional classification system and a deep reinforcement learning version of convolutional neural networks has to do with the max pooling feature. So in traditional networks, as I mentioned at the beginning, max pooling is used a lot. It reduces dimensionality, and it, more important, gives you that translation independence. In the especially like in Atari, as an example, game screens, you really don't have to worry about that translational independence. You always have the same game screen coming in as input. Things are always going to be, in the places where they are in that screen, and so the authors of the paper they chose to eliminate the max pooling part of that. They could have kept that in there still, to provide the dimensionality reduction and some of the other features that max pooling provides, but they chose to pull that out to probably just to help improve the computation or reduce the computation that they would have to perform. It'd be interesting though to recreate their problem today and add the max pooling in and see what kind of differences you might see. Well, that's all I really had to talk about this evening. So I hope everyone found this valuable, and if you're familiar with convolutional neural networks and classification problems, then you really know also how to use them to create the same sorts of features as input as the state space for a deep reinforcement learning problem. And with that, we'll close for this evening, and we'll talk to you all next week. Bye.